Okay, so section 13.4 is on velocity and acceleration. And it starts with something, or at least we're going to start with something that seems like a side issue. Which is projectile motion. And I'm not sure why they put it in other than they feel like, well, that's velocity and acceleration, right? So just as a reminder, projectile motion or any motion at all has R of t equal to position R prime of t equal to velocity, which we'll also refer to as V of t. And R double prime as acceleration, which is obviously V prime of t and A of t. Okay. And if we assume, if we do projectile motion with constant gravity, and no friction, then it's easy. If you put non-constant gravity, like if you're trying to put a rocket in orbit, then you can't assume constant gravity and you can't assume there's no friction. So the engineers that do that problem, their math is a lot more advanced than what we're doing right now. It's all vector calculus, but it's more complicated vector calculus. So we're doing sort of intro. This is like baby math. I mean, we feel like you've learned so much, but we're actually just getting to the point where you could open it up and actually do some of these super hard problems with vectors. But let's just go ahead and say constant gravity. So gravity is acceleration. Okay. And so I'm going to do R double prime for gravity. It's constant, so let's just call it 0, negative g. And of course, g is going to be 9.8 meters per second squared in metric, or let's say 32 feet per second squared in imperial units. And so then what we just want to do is to find a position function. But it'll be a vector function. For position, this is a differential equation, and it's a simple one because you can solve it by taking two antiderivatives. So what's different about this differential equation from other differential equations you've solved is that it's a differential vector equation, or maybe I should say a vector differential equation, which sometimes they'll just abbreviate as a VDE, vector differential equation. But we're just going to do the easy two antiderivative solution, which you can have a lot harder differential equations than that. Some initial info would be the initial position will be R naught. And that's just going to have an X naught, Y naught position. So we're just doing two-dimensional. And of course, this will be R at time 0. Initial velocity will also need to be known. So this would be V naught, which is going to be, yeah, I think I'll just call this R prime at time 0, or if you like, you can call it V at time 0. Okay, so that's all the kind of the starting information. So let's solve the differential equation. Oops. Okay, so again, you start with the equation, which just says r double prime of t equals 0 negative g. And we take antiderivative, so r prime of t will be, oh, and by the way, can I just call this vector g for gravity? Okay, so r prime of t will be g t plus a constant, I'll call it c1. The vector, the constant has to be a vector with this kind of an antiderivative. Okay, now when you do I prime at 0, you're going to get a 0 vector plus c1. And of course, this has to be equal to v sub 0. So that tells us that c1 is v sub 0. So now we can say r prime of t is gt plus v sub 0. Okay, so I guess part of this is just for you to see that vector differential equations have a really similar, solving process as a scalar differential equation. Nothing here is different from what you would have done if you had assumed it was a scalar function and just said, y double prime is equal to negative g or whatever. Just take two antiderivatives. Okay. But of course, we need one more antiderivative. So now we can say r of t, which is our position function, would be 1/2 the vector g times the scalar t squared plus the vector v naught times the scalar t plus another constant we'll call c2. Okay, and of course r of 0 will just be 1/2 g times the scalar 0 squared plus v naught times the scalar 0 plus c2. Of course, that's c2, which needs to be initial position because this is position at time 0. So we'll just call this r sub r naught. Like that. So yeah, c2 is r naught. Okay, any questions? I'm going to clean that up just a skosh. Okay, are there any questions? It's pretty straightforward. Okay, so therefore we can say r of t is 1/2 gt squared plus v naught t plus this c2, which is our r naught. Okay, any questions about that? Okay, and that it looks just like the equation for motion, projectile motion in a physics class that you normally cover with a scalar function. Okay, now, but what we probably want to do here is to start analyzing this. So I think we've described R naught, we've described G, but we haven't described what V naught looks like. So again, V naught is gonna be this vector. We have a projectile that's being launched, and of course it's going to follow a parabolic path like that. But it's going to be launched with some initial position. Let me see if I can get that straight. And initial velocity. So let's give this thing an initial velocity vector, maybe pointing like that, I guess. Okay, so that'll be my v sub 0. And we're going to define this in terms of an angle of inclination. So I'm going to give a horizontal here and call this angle theta, like that. And let's go ahead just for the heck of it and say that script v naught will be the magnitude of the vector v naught. So therefore, we can step back and say, all right, v naught, the vector, is going to be script v naught cos theta, script v naught sine theta. Okay, any questions about that one? Okay, so we can really pull this all together. Let's just go ahead and say that R of t has an x of t, y of t component, two functions of t. And again, these are 1/2 g t square plus v naught t plus r naught. And then I wanted to just look at the components of these. So this is giving 1/2. G was just 0, negative scalar g, plus v naught, which is going to have the script v naught cos theta and the script v naught sine theta. So that's times t. Oops. And then the r naught is the x naught y naught. Like that. Which I think I want to combine into a single vector. Oh, I don't have my t square there. So let me fix that. And the other one has a t, so I guess I'm okay there. Okay, so just to combine these into a single vector, you would have no x component for the acceleration part, but we would have a script v naught cos theta times t. Plus x naught, comma, and then the negative 1/2 gt squared plus script v naught sine theta times t plus y naught. Okay. And so, of course, you have these are the x and y components. So the first one here is our x of t. And the second one is our y of t. Okay. So maybe I'll just go ahead and put it down here. X is this first one. And y is the second one. Okay. And then we usually mention that the problems are easier, obviously, if x naught and y naught are 0, things factor out and stuff like that. So just go ahead and say usually x naught is 0 and y naught is 0. Okay, but it doesn't have to be that way. But most of the formulations that you see for other formulas that follow have that initial launching point of 0, 0. So it's sort of this is a parabola that goes through the origin. Okay. Any questions? So we got the starting point at 0, 0. Okay, down here, the x-coordinate will be the range, and the y-coordinate will be 0. There. And to find the range, you would just set the y-coordinate to 0, right? So for the range, set y equal to 0. Remember, y naught is 0 also. So we'll just do -1/2 gt squared plus script v naught sine theta times t and set that equal to 0. And then we'll factor it. So we'll have t times -1/2 t plus script v naught sine theta equals 0. That gives two solutions. The first one is t equals 0, which of course is the starting point. And the second solution has what? T equals 2 v naught sine theta. Like that. So this is the time. Any questions yet?
Nope.
Okay, so at this time, we need x. Okay, so that'll give us the range. So x, which is our range, will be equal to script v naught cos theta times t, where t is what we wrote up above, 2 script v naught sine theta. Okay, and remembering that x naught is 0. Okay, so here, I feel like something's missing.
Where did the gravity go?
That's what I was wondering.
Okay. I'm a little bit behind and I'm trying to write, and then I was like, wait a second.
I'm behind too. It's like, wait. So let's put our gravity back. I was like, I thought there was supposed to be a denominator on this thing. So is this all over gravity? Yeah, so the gravity ends up down below, and I feel better now. Like that. Okay, thank you for catching me there. So in the end, this is gonna be, it looks like there's a 2, a v naught square, and then there's a sine theta cos theta over gravity. Okay, but you know that 2 sine theta cos theta is what? I know you know, you won't say. Okay, fine. So sine 2 theta. So let's just put that in and we'll call it the range would be script V naught square sine 2 theta over G. Okay, and then they can ask all kinds of questions like what angle maximizes the range? So let's do a couple of questions about this before we go on. So what angle theta gives maximum range? This is easy. You don't need to take a derivative. What should we do?
The derivative is 0.
A little louder? What'd you
I mean, the derivative become to 0.
Yeah, so what we want sine of 2 theta, the biggest that this can be is when sine of 2 theta is 1, right?
Yeah.
So we want when sine 2 theta is 1, that's you're never going to get any bigger. Remember, theta is the variable right here. So we want 2 theta to be pi over 2, right? So theta is pi over 4. Which is 45 degrees. And I think if you think about it, that makes a lot of sense. Okay, any questions there? And how about this one? If a projectile is fired at 450 meters per second, give two angles that allow the projectile to hit a target 2,500 meters away. And if that's also strange, but you want to kind of think of it kind of like both these curves are supposed to be under gravity, but so I'm going to draw two of them. And I think the idea here is that I'm going to put a vertical in to make these look nice. Hang on. Looks like Star Trek. I don't think I can do this. It's okay. I don't know why I'm trying so hard. Oops. The idea is there's two angles that are on sort of opposite sides of 45 degrees. So let me put the 45 degree in there. So 45 sort of gives that optimal angle. Let me see if I can do this better here. I'm gonna set it lower. So this is better, I think. And these tend to be symmetrically on either side of 45 degrees. Okay. So we're trying to find this angle, theta. Ooh, not that angle. It's two different angles, right? So this one that I was drawing is the 45-degree angle. Okay, but that's not what we're looking for. We're looking for the other two angles. So all you got to do is solve this trig equation. So you take the range. Put in the velocity, initial velocity, which is 450. That gets squared. And then we're going to have sine of 2 theta, which was, we're hoping to get 2 thetas out of that, and divide by gravity. This is in meters, so we're going to have to use 9.8 for gravity. Okay, so let's go ahead and say the sine of, sine of 2 theta is going to be 9.8 over 450 squared. Okay, so I think we can do this in degrees. So 2 theta is going to be sine inverse of 9.8 over 450 squared, like that. So again, let's do that in degrees. Okay. So if we do sine inverse of 9.8 divided by 450 squared. No, this is, I wonder if I'm doing something wrong here. Zero, zero. I think I'm making a mistake somewhere.
I'm getting 0.0027.
Yeah, that's why I'm trying to figure out what I did wrong. So let's see if we can get this straight.
Well, isn't your range 2,500?
Yes.
So then it would be 2,500 is equal to.
Oh my gosh. Yeah, thank you. That's just a shame. Why did I do that? Okay, so forgive me, everybody. I don't know what I'm doing. My brain must be off. So we're setting this equal to 2,500. Thank you. Okay, so then we can say sine 2 theta. Don't ever do that. Is 2,500 times 9.8 over 450 squared. Oops. So 2 theta is sine inverse of that. Okay, let's try. Hopefully I can just go back and edit that last one and put a 2,500 in there. And get an angle that looks a little more reasonable. Okay, so anybody have that one?
$6.95.
Yeah, let's go 6.95 degrees. That looks great. Now that's only one of the angles. Remember, that's 2 theta, so we'll divide that by 2. But just if you think about a unit circle, you know that there's 2 quadrants where sine is positive. Okay, I'm trying to center this. Hang on, right there. Okay, so if this is angle right here is 2 theta, like that, then this y coordinate that I've just drawn is the y coordinate that is the sine. But if I go horizontally over to the other side, I get the same y coordinate. So there's another angle over here that I need as well. And so this angle here is going to be like 180 minus 2 theta. Okay. So 180 minus 2 theta will be 180 minus 6.95. Okay. Which is 173.05. Both of these have to be divided by 2. So the angles of inclination are 6.95 over 2. Oops. Okay, so, and I've done this with the unrounded. So it's 3.47 degrees, and the 173.05 over 2. So that's going to be the 86.53, I guess, degrees. Okay. And so again, if you just kind of refer to that first picture there, you've got one that's shooting up real steep, the other that's shooting down low. One's greater than 45 degrees, the other one's less than 45 degrees. And they both hit the same target. Okay, any questions about that one? Let's see, 751. Let's get through the rest of this. So just for the moment, I'm going to pause and give you a second to catch up. Because we're going to leave the projectile motion behind. And we have to do vector functions again and space curves. And I think we can make this pretty quick. Okay, so like I say, this is back to space curves. Just as a reminder that we said that that if just a couple of things, R of t is position. Don't forget that the unit tangent is r prime over the magnitude of r prime. like that. And so one of the things we did was we said, well, so R prime is the magnitude of R prime times the unit tangent. Okay. And if we take a derivative of that, this allows us to look at acceleration in our new sort of coordinate system that involves the unit tangent and the unit normal. So watch how this breaks out. And also, I guess I should also recall that since t has constant length, that t prime is perpendicular to t. Okay. So if you do r double prime, this is all sort of, this was in the last section. R double prime is the derivative with respect to t of r prime. And I'll go ahead and say, well, that's the derivative with respect to t of what we wrote r prime was. That's the magnitude of r prime, which gives the length of the vector, and the unit tangent gives the direction of the vector. Now, those are both functions of t, so we have to use the product rule. So here, oh, and another thing, I should also remind you, oops, that one of the other things we came up with in the last lesson that was that the magnitude of r prime is speed, okay, which is the rate at which arc length grows as you move along a curve. Okay, so S is arc length, ds over dt is how fast your arc length is growing, which is just another way of describing speed. Okay, so here I want to write this as d over dt being operated on a magnitude of r prime, which is ds over dt times the unit tangent. And now here comes the product rule. So we're going to say d2s over dt squared, okay, times t, plus we're going to have a ds over dt times t prime. And again, t is a unit vector, but t prime is not, and that's why t gets a hat and t prime gets a barb, because once you take that derivative, it's not going to be a unit vector anymore. And that just depends on how fast t changes direction. Okay, any questions with that? So I want you to notice that this is two components of acceleration. This is a tangential component. And this part is normal, which is perpendicular to the tangent. Remember, t prime is perpendicular to t. Okay, and my goal here was to express acceleration in terms of two parts. One part that's tangential and another part that's normal. So this is getting me where I want to go. I think I go ahead and write down d2s over dt squared, and I actually don't have any complaints about this. I'll just leave the t here. But this ds over dt, I want to get the unit normal involved. So I think what I want to do is remind you that the unit normal is t prime over the magnitude of t prime, like that. So let's do that. Maybe, oh, so from here I could say that t prime is the magnitude of t prime times the unit normal. like that. So what I have here is plus ds over dt. And the magnitude t prime I'm going to put here times the unit normal. Now I'm expressing things with my t and the coordinate system. I've already said that the normal component of acceleration is what causes curving. So it makes sense to bring in curvature here. So next thing I want to remind you here is the kappa. The very first formulation was the magnitude of t prime over the magnitude of r prime. Okay, so t prime, magnitude of t prime is the magnitude of r prime times kappa, the curvature. Okay. So that means I'm going to keep this d2s over dt squared times the unit tangent. Plus, I've got this ds over dt times the magnitude of t prime, which is the magnitude of r prime times curvature times the unit normal. Okay, and the only other thing I need to add to this is to remind you that the magnitude of r prime is the speed. That's the rate at which arc length grows as you move along a curve. So that's another ds over dt. So then we can step back and say, okay, so therefore, this is equal to d2s over dt squared times t plus this is the ds over dt quantity squared times kappa times n, like this. And then the final thing is to remind you that kappa is 1 over rho, which is the radius of curvature. Okay, so we say d2s over dt squared times t plus, let's do it this way, ds over dt quantity squared divided by rho times the unit normal. Okay, so that's everything. Acceleration, a of t is r double prime of t. Okay. And we're supposed to get meaning out of this. So this is the tangential part or tangential component. Of acceleration. Okay, and the other is the normal component of acceleration. I said tangent, but I should have said tangential. Okay, and the other normal component. Okay. Now, let's look at these individually. The tangential component is going to be AT. It's going to be d2s over dt squared. Which is the derivative of speed. You want to think of it as d over dt of ds over dt equals d over dt on speed. Okay, now that to me makes a lot of sense. When people think of acceleration, they're usually thinking about how their speed is changing. So really they're thinking about the tangential component of acceleration, which is not all of the acceleration that is experienced as you move. That should not have a, I'm removing the dot between those two differential operators. Okay. It's the tangential component that changes or causes the change in speed. The normal component of acceleration is an. Okay. This had several forms. I could call this the first form up above, which was ds over dt squared times kappa, which is curvature. And notice the close relationship between curvature and the normal component of acceleration. In fact, they're directly proportional. If you double the acceleration, the normal component of acceleration, then it doubles the curvature. So it just makes a sharper turn. Okay, so the normal component does that. But the acceleration, you need to multiply speed squared times curvature, or better, ds over dt squared over rho. That's a physics formula. So what's speed? Remember, rho is the radius of curvature. So maybe I should bring that picture back down from way, well, no, it's a different section. So I'm going to copy the right picture over real quick to remind you. I'll come right back here. Where is this? Yeah, this is good. Maybe I'll leave the heart out though. So rho is the radius of the oscillating circle, which has the same curvature as the curve that you're studying. Okay, so what you have for the normal component of acceleration over here is speed squared divided by radius, right? What did you learn in physics is speed squared divided by radius. I know they say velocity square over radius, but what's it called? What's v squared over r in physics?
Is it centripetal acceleration?
Correct. This is centripetal acceleration. So acceleration is composed of two parts. So this is the decomposition of acceleration. Okay, that acceleration, which of course is just r double prime of t, has a part that is tangential. At is the scalar component of the tangential, the scalar part of the tangential component of acceleration. And then an is the normal part of, sorry, I should say an is the scalar part of the normal component of acceleration. Okay. So again, AT is d2s over dt squared. This is the change in speed. Maybe let's just say d over dt times speed. Time, not times of speed. Okay, so this is responsible for changing speed. And then AN, it had a couple of formulas that I'll copy down here. So AN is ds over dt squared times kappa which is the same as ds over dt squared divided by rho. So this is centripetal acceleration. So this is responsible for curvature. I'll say change in direction. And they're both buried in the acceleration vector. They add to make a single acceleration vector, which is really weird because they're sort of two different things, except for you experience them together, right? When you accelerate by just going forward, by increasing your speed forward, you get pushed around, but you feel the same thing when you go around a turn, you just get pushed out of your position. So what you experience, those two things combine to have one sort of physical sensation. And of course, that's your acceleration. The combination of both of these. And almost is, with your eyes closed, they're almost indistinguishable from each other. Okay, but they do break down this way. So is there any questions about that? Maybe a side note here. I'm gonna have to do this on a separate page. So on the side, I think I'll add, first of all, that if you have A acceleration is AT times T plus AN times N. If you dot both sides with T, you get another formula for AT. So if you do A dot T here, you get AT times T dot T plus AN times N dot T, like that. And what's T dot T? I'll give you a hint, it's the magnitude of T squared. So what's that?
1.
And what's N dot T? Somebody? Those are perpendicular, right?
So
So
G is 0.
Yeah, so perpendiculars have a 0 dot product. And so this tells us that AT is just A dot T. Okay. Again, that's a scalar. So dot products result in scalars. This should not come out as a vector. I might remind you that A is R double prime and T is R prime over the magnitude of R prime. I'm sorry about all these formulas, you guys. So we often write the formula for AT as R prime dot R double prime over the magnitude of R prime. So you'll see that come up when I do a summary. So that's one formula for AT. And you could say likewise, we won't use this one because it's really hard to compute in, but likewise, it turns out that AN is A dot N, just like AT is A dot T. Okay, so that's just a side note that we won't use. And if you had A and N, it would be easy to do AN by doing that dot product. Okay, so just real quick, the other formula for AN up above is ds over dt squared times kappa. Okay, you may remember this is the magnitude of R prime. ds over dt is the magnitude of R prime, so squared. And then kappa is the magnitude of R prime cross R double prime. You've seen this before. Over the magnitude of R prime to what power? Does anybody remember?
Third.
Yeah, to the third, right? So when you write that out, this actually looks a little bit like the formula for AT. So this is the magnitude of R prime cross R double prime. Because of the cancellation, you just get over the magnitude of R prime. Okay, so let's do a quick little summary of all this. Okay, so the summary is that AT, well, first of all, A is AT times T plus AN times N, like that. AT has now several formulas. It's D2S over DT squared, which I think I'll go ahead and make very clear. That's the derivative of the magnitude of R prime, just to make sure you understand. Because ds over dt is R prime. But this is also R prime dot R double prime over the magnitude of R prime. And this can be positive or negative. If you're slowing down, your tangential component of acceleration will be negative. Okay. AN now has a couple of forms. Is that all I had? I think that's everything. AN has a few formulas. Okay. It is ds over dt squared over rho, or you can write that as ds over dt squared times kappa, almost the same formula. But we also showed that this is the magnitude of R prime cross R double prime over the magnitude of R prime. Okay. And you see the symmetry in those two formulas, very closely related. And there's trig behind the scenes there with the dot product and the cross product. The dot product doing a cosine to get one part of a triangle. And I guess you could kind of break accelerate, basically if you have a turn like this on a path, and then there's an acceleration vector associated with it. If it's turning, then the acceleration vector might point in like this. So that's acceleration there. Okay, but we're saying that there's a tangential and a normal component of this. So you can draw a triangle like this, I suppose. That's no good. Let me try a little bit harder. Something like this. That's a little better, I guess. Okay, so the acceleration vector, actually, I think I'll put the A right here. Okay, and then the normal part is AN times N. That's a vector if you multiply it by N. I can't write small enough. AN times N, like that. And then the tangential part going this way is AT times the unit tangent, like that. And if you wanted, you could put another copy of that up and make it look tangent to the curve. So I'll go ahead and copy that up here. Like that. Except for I better, I think I'll move that just a skosh, like that, and put it into position. Okay, so tangential component, normal component. Obviously, this is a right triangle. So there's trig behind the scenes here. But as usual, the dot and cross products are doing our trigonometry for us in three-dimensional space, which is very complicated. The dot and cross products do the trig for us, so we can break down acceleration into these two vectors that basically add up to a right triangle. Okay. How are we doing? 8:20. Let's see if we can squeeze in a quick example. And then we'll call it a day. I'll talk a little bit about your exam. So, example. Load of stuff. R of t is root 2. Root 2 with a t next to it outside of the root, and then an e to the t and an e to the negative t. That's kind of cute. R prime of t is just going to be root 2, and then I'll have an e to the t and an e to the negative t, like that. Okay. Magnitude of R prime of t. Well, here goes. So I'm going to have that root 2 square plus e to the t square plus e to the negative t squared. And I promise you this will be a perfect square. Okay, it's going to be 2 plus e to the 2t plus e to the negative 2t. And just to let you know, if you do e to the t plus e to the negative t squared, you get e to the 2t plus 2 plus e to the negative 2t. Okay. So this is a perfect square inside. And if you look at this thing, you can kind of see there's a perfect square there. Okay, so this thing is just the square root of e to the t plus e to the negative t. And I'm warning you on the exam, watch for the perfect square. It will be there. Okay, so you just end up with e to the t plus e to the negative t, and that's the speed. Okay, and you may note that speed is always positive, but the derivative of the speed can be negative because you can slow down. Okay, speed is never negative. It can be 0. Okay, now let's go ahead and do r double prime. of t is going to be 0 e to the t. Do I have a mistake? I did. Did anybody catch my mistake up above?
The derivative. Go ahead.
Go ahead. Go ahead.
I was gonna say the derivative of e to the negative t.
Right, so I'll put the minus sign in green there. And I guess I can put it down here also. Thank you. Well, you should have told me. It's not your fault, it's my fault. But don't feel shy about interrupting me, please don't. Okay. So anyway, so that minus sign is going to be positive now, so I'm going to have just an e to the negative t next for the velocity. So the minus sign's gone. Let's do our dot and cross products real quick. So if we do r prime dot r double prime, so you'll have, I'll just write it out. You're going to have root 2 times 0 plus e to the t times e to the t, and then plus negative e to the negative t times e to the negative t. So I think you're getting e to the 2t minus e to the negative 2t. Okay. Any questions? That's the dot product, which we'll use for the tangential component of acceleration. And the cross product, magnitude of r prime. Well, I'll do the magnitude later, my bad. So let's just do r prime cross r double prime. Okay, so yeah, my r prime had the root 2 e to the t and a negative e to the negative t. And then my r double prime had the 0 e to the t and e to the negative t. Put ijk up on top. Like that. Am I kidding myself by thinking I can squeeze this in here? Maybe. So let's see here. For the I component, I multiply like that. And I don't know, but I think I get 1 when I do e to the t times e to the negative t. And then there's minus a negative 1. So I think it's just 2. I times 2. Minus j. Okay. Let's see here. So we're going to go this way. And I think we just get root 2 e to the negative t. Like that. And then plus k. Looks really similar. I think we're going to go this way and get root 2 e to the t. That's easy. So let's write it one more time. R prime cross R double prime is the vector with a 2, negative root 2 e to the negative t, right? Now it's positive, it's negative, and then a root 2 e to the t. Okay. Now we need the magnitude of this. So the magnitude of r prime cross r double prime is going to be the square root of the sum of squares. So we're going to do a 2 square, which is 4, and then squaring the next one, you're going to have plus 2 e to the negative 2t, and then plus 2 e to the positive 2t, like that. Maybe factor out the 2, you'll see. So this is the same square root we had before. You have the 2 factored out, and you've got you could write it as e to the 2t plus 2 plus e to the negative 2t. There's that perfect square we had before. So maybe I'll write it as the square root of 2 times e to the t plus e to the negative t. That quantity is squared. And then you can wrap this up by just saying this is the square root of 2, and it's times e to the t plus e to the negative t. And of course, this is always positive as well. Okay. Now let's just kind of wrap up with the very last bit here and say AT is r prime dot r double prime over the magnitude of r prime. Okay. So r prime dot r double prime was e to the 2t over e to the negative 2t. Sorry, my bad. E to the 2t minus e to the negative 2t. That's what I should have said. Over the magnitude of r prime, which I have no idea where that is. It's e to the t plus e to the negative t. Should I stop there? Answer is not if you want full credit. The numerator is the difference of squares, so you should write this as e to the t plus e to the negative t times e to the t minus e to the negative t over e to the t plus e to the negative t. So the answer for the acceleration, the tangential component of acceleration is e to the t minus e to the negative t. And you can see that can be positive or negative. So again, speed is always positive, but the tangential component of acceleration has to be positive or negative, so you could speed up or slow down. Okay, so you can see that could go negative if the second term is bigger. Now, an is the magnitude of r prime cross r double prime over the magnitude of r prime. So let's find that. I know the denominator. The numerator is up there. Oh no, it's right there. So it's root 2 times e to the t plus e to the negative t. And that's very closely related to the speed, which was e to the t plus e to the negative t. So the normal component of acceleration is just root 2. That looks constant. Okay. So the curvature, sorry, the normal component of acceleration is the same everywhere. You're tempted to say that because the normal component of acceleration is the same everywhere, that the curvature is the same everywhere, but it's not, because the speed is increasing. If you look at the speed function, it's getting bigger. So if you apply the same amount of normal acceleration over an increasing speed, that makes the curve get wider and wider. So it does not have constant curvature. Anyway, that's all we have time for on this. So I'm going to go ahead and stop the recording and just say a few things.